Hello, beautiful people, and welcome. In today's video, we're going to go through some notes for radical and rational exponents. Let's go ahead and start out what radicals are. A radical is the following symbol. We have the most common radical, which is the square root. Then we have a radical that is a cube root. And then we have things of nth root. An nth root is where you have any number in that specific location. So we typically say that it's an nth root where n is a variable that represents something. Then we have here our rational exponents. Now we know what exponents are, but rational means fractions. So what we'll end up seeing is when we have x to the nth power, this will end up being a fraction. Now, somehow radicals and rational exponents have a relationship with each other. And so this is called conversions. So let's go ahead and start converting from a radical to a rational exponent. Let's start with our very common square root. So if, for example, we have the square root of, let's do something like 9. A square root of 9 means that there is something called an index, which is the number that we see or don't see on the outside. What I like to refer an index as is the house number. So if you have a house, the number of your house is your index. If you don't see an index, that means mathematicians are lazy. And we do, yes, have an index. And that index is 2. So for example, the square root is so common that we actually don't write an index here, but it is 2. Next, we're going to take a look on the inside of our root. And we're going to take a look and see, does this have an exponent? If no exponent, that means yes, there is an exponent. And that is 1. So sometimes you do see an exponent, sometimes you don't see an exponent. If you do not see an exponent, that means that it is 1. So let's go ahead and rewrite this one more time. We have an index of 2 as part of our square root. Again, that is a secret 2. You won't see it. We do, yes, have an exponent of 1. And so to rewrite it from a radical to a rational exponent is we are going to take the base. Then we are going to take the exponent. So basically everything that you typically see. Here's our exponent of 1. Now the trick here is with the index. The index is always going to be your denominator. So let's write this one more time. The square root with an index of 2, exponent of 1 of 9 is the same thing as saying 9 to the power of 1/2. Now, sometimes they'll give you things like a variable where you're not actually going to solve anything. So we know the square root of 9 is 3. So 9 to the 1/2 power is also 3. But sometimes they'll give you things like x's and a's and y's. So let's do example 2. We're still converting from a radical to a rational exponent, but sometimes they'll give you things like, let's say, cube root of x to the ninth power. To rewrite this, we are going to be taking our base. Here's our base of x. We're going to take exactly how we see the insides, 9, which is our exponent. And we're going to take our index, and index is always going to be our denominator. Now, yes, you can simplify this. So I'm going to put a box around this. This is converting. If we wanted to simplify, you would then proceed to divide. And we would get 9 divided by 3 is 3. Right now in this section, I am asking you just to convert, and then later on, we're going to spend some time simplifying. Let's do one more example. Now, sometimes what they'll give you is they'll give you, let's say, the 5th root of now let's do 3n. And then all of this is going to be raised to the 2nd power. Now, a little bit different. So let's take a look at example number 1. Example number 1 had numbers. We got a 9, we got a secret 1 as an exponent, we got a secret 2 as an index. Here we had a variable x, we had an exponent of 9 and an index of 3. Here we have a combination with a number, letter. We do not see an exponent on the inside. Yes, we see an exponent on the outside, and then an index of 5. What's really cool about radicals is it doesn't matter where that exponent is. If you see the inside, 3n, that is going to be your base. So all of your inside is your base. Do not separate 3, do not separate n. But because we have multiple things on the inside, we have to put this in parentheses. Otherwise, when you give it an exponent, the exponent will only affect n and not 3. With parentheses, the exponent will be on n and will be on 3, just like this 2 exponent is on everything. Then we pick up our index. And again, our index is always the denominator. So we have, I'm just going to write this out one more time. We got open, 3n as our inside. The exponent is 2. The index is 5. Now, if we're going backwards from a rational exponent to a radical, let's do example number 4. So let's say we are given x to the power of 9/5. And we want to convert this to a radical. You're going to pick up the base, whatever's on the base of your exponent, that's going to be on the inside of your radical. Then you're going to make a decision. You can either take this exponent, write it on the inside. You can choose to do parentheses. You can also choose not to do parentheses, kind of like we did in example number 2. There was no parentheses on the inside. If you want to write them in, you can. And then we take a look at our index. Index is going to be our denominator. So we can write this as with the parentheses. We can write this as without the parentheses, or we can actually put the parentheses all on the outside and then have our exponent of 9 all on the outside. So the exponent, again, can be inside. The exponent can also be outside, and it does affect it the same way. Let's go and do one more. Example 5. Now, I want to talk to you about negatives. Let's do one positive and then we'll talk about negatives. Here, let's do one more as k to the power of 5/4. Again, inside is k. That's our base. Let's draw the radical. The denominator is always our index. So we have an index of 4. What's always on top? Well, always on top is our exponent. So we have a choice to make. We either write it inside as an exponent, or you can write parentheses, index of 4, k is our base, and then you can write the exponent of 5 on the outside like this. All right, let's talk about negatives. When you have a negative, this goes back to your integrated math 2 or even your integrated math 1 lesson for your properties of exponent. So when you have an exponent that is negative, what this negative does is it takes the base, takes the exponent, and it takes the reciprocal. We typically say we flip the base. And this negative, I want to be very clear, this negative gives you directions. And the direction is to flip or take the reciprocal. That spelling is throwing me off. But if we take the reciprocal, that's only when we have a negative exponent. Do not do any flipping. Nope, spelling is good. Somehow that threw me off. I had to Google it real quick. Okay. For example, how does this affect your conversions from a radical to a rational expression? Example 1. So let's say we have m to the power of negative 2/3. We are going to treat this as taking the base, taking the exponent, ignore the minus, this right here. We're going to see m. That means we're going to flip m into 1/m. We're going to take our exponent of 2/3 and we're going to keep the 2/3 with the m. Notice I'm not flipping 2/3. I'm not doing anything. All I am doing is using this negative as directions to flip m. Okay, now m happened to have an exponent, so that's fine. Take the exponent with it, but you are not flipping the exponent, you are flipping m. You are taking the reciprocal of the base. Now that we are here, then you're going to take this 1/, and we're going to write our base of m. You're going to have a radical. The exponent is the number on top. The index is the number on the bottom. So our index is 3, and our exponent is 2. Now, again, you have a choice to make. You can either write this on the inside or the outside of m here. Now, in future lessons, I am going to show you that having a radical in the denominator is not a good thing. But right now, what's our goal? Our goal is just to convert, not to simplify. So we're just converting. Let's go ahead and try this again. So what happens if we see 1/5 of 3n? Step number 1, you're going to convert the radical into a rational exponent. So what's my base? My base is 3n. So I'm going to write 3n. What's my exponent? Well, I don't see any exponents anywhere. Remember, if there is no exponent, you can have a secret exponent of 1. You can have the secret exponent of 1 here as well on the inside. And then our index, always the denominator, is 5. Now, because we see the rational exponent in the denominator, we are going to go backwards. Notice how I have 1 over m that came from just m. 1 over m came from just m. So I am going to flip this into just 3n with a negative, be careful here, negative exponent. So this exponent here of 1/5 is positive because I am no longer having it in the denominator. You can even do this. So I'm flipping, putting the 1 on the bottom, 3 on the top. The negative has to be there. Okay, so if you're taking something and putting it in the denominator, taking the reciprocal of the base here versus we are in the denominator taking reciprocal of the base, here we are with a negative exponent. Okay, now let's talk about our next section, which is simplifying. I'm going to go ahead and separate this. So everything we've done so far is called converting from rational into radicals and radicals into rational expressions. Simplify. Two things that we're going to talk about when we're simplifying. When we're simplifying, you always want to simplify your fractions by splitting them up. So two things, split up your terms, split everything up with multiplication. So first thing, when we're simplifying, we want to split everything up with multiplication. Second thing you want to do is you want to find and evaluate the perfect whatever roots we have. So for example, if we have the 7th root, we want perfect 7th roots. If we want to convert to fractions, we can. So find perfect roots. Okay, let's go ahead and start with an example with our very basic square root. 2 root, and you want to extend this out because we have a couple things, 72 m squared p and q. You're going to first split everything up into multiplication. 2 times the square root of 72 times the square root of m squared times the square root of p times the square root of q. Now, if there is no index, it is very helpful to write in the index. So our index is missing. So that means if you have an index missing, the index is 2 for your square root. Next, you're going to find perfect roots. So let's work on the one with the numbers. And you want to split this up into a perfect root using the largest number we can find. So I usually recommend go ahead and do this off to the side. And you're going to quickly generate up to this number, but not going over this number, your perfect roots. So we have 1 squared is 1, 2 squared is 4, 3, 4, 5, 6, 7, and 8. I'm not going to write 9 because I know 9 times 9 is going to be too large. And this takes you a few seconds, and you have a calculator to help you with this. And you can just type in the squares. Let me find my calculator. So for example, we can just do 3 squared which is 9. So the square root of 9 is 3. 4 squared, we got 16, then 25, then 36. 7 squared is 49. And then we got 8 squared is 64. Now, when you are simplifying your radical, you're going to take that number, 72, and you're going to find the largest perfect square that goes into, well, you guys can't see, that goes into 72. So 64 is not a perfect value for 72. Then I go to 49 is not a perfect value. Then I go to 36 is a perfect value. So 72 and 36 do get along. So I'm going to split this up into 36 times 2. This 72 no longer exists. I still have this 2. That's still here. And now I'm going to continue to simplify my variables. Now, when you break this apart, I'm going to ask you to write out your variables that many times. So if I have an m squared, I'm going to write it m times m. This is just 1p. This is just q. To simplify your variables, you are going to look at your index. So I have an index of 2, and this is how you're going to be grouping your variables. And your question is, how many? How many groups do you have of 2? Because our index is 2. And are there any leftovers? So I have one group of 2. So that means I'm going to have m to the first power to simplify. My index is 2. How many groupings can I do? I can do one grouping. Therefore, I can simplify this. I will show you a different way in just a few moments. So what do we have now? Let's bring everything down. We have 2 times the square root of 36 times the square root of 2 times just m. Do I have any leftovers with m? No. I just had 2 and I have 2, so that goes away. That's gone. I cannot do a grouping of 2 with just 1 p, and I cannot do a grouping of 2 with just 1 q. The only thing left to simplify is that 36. The square root of 36 is 6. And now one last time, I'm going to rewrite this before our final answer. Just like that. Let's go ahead and do our multiplication. Notice I have 2, 6, and m to the first power. That is not inside of a house. So we got 12m. And then what do we have inside of the house? Well, the house number, the radical, has all index of 2. So that means the house number is the same. So 2 lives inside of the house, P lives inside the house, and Q lives inside the house. Okay, and this is our answer. Let's try this again. Example 2. Let's do something of higher power. I have -3, the 7th root of 640, P to the 12th power, Q to the 8th power, and R to the 6th power. First thing you're going to do is you're going to split everything up into multiplication. Remember that you do have a 7th root on this one. So everything has to have an index of 7. Okay, next you're going to take a look at your numbers. So not the variables, but your numbers. Off to the side, you're going to write out your perfect sevens. Now, we are not going to be typing in a squared here, so we have to do, let's see where you can see it. You can see it here. You're going to do to the 7th power. So we still are going to have 1, 2, 3, 4, 5. Let's do our radicals. 7th root. So not square root, but now 7th root. We do have an index. So I'm going to do 1 caret 7. That's 1. 2 caret 7. That's 128. 3 caret 7. Oh, that's too big. 2,187. Now, I'm not going to do 4 and a 5 because I already noticed that 2,000 is well over 640. We don't want to go over that number. So I don't even need to have this number. So I'm going to check if 128 goes into 640. Yes, it does. So I'm going to split up. So now I have a 7th root of 128 times the 7th root of 5. That means I no longer have the 7th root of 640. Let's bring everything down. And then we're going to focus on our variables. For our variables, I'm going to need some space. So I'm going to say 7th root of p to the 12th power. We're going to write this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And my question is, well, how many groups of 7 can I do? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5. These are leftovers. So what happens is you have the 7th root of p to the 7th power times the 7th root of p to the 5th powers. So if your index and your exponent match, this is 1, okay? A reason for that is if we were to convert to radicals, if we were converting the radicals into rational exponents, this is my exponent of 7. This is my index of 7. 7 divided by 7, we just get p to the 1st power. So if you wanted to use conversions, you can. If you wanted to use groupings, you can. Now this leftover, we have no choice. That's just our leftovers. Next one we have is 7th root of q to the 8th power. So we have how many groupings of q? 1, 2, 3, 4, 5, 6, 7, 8. I want groupings of 7. 1, 2, 3, 4, 5, 6, 7. That means I have 7th root of q to the 7th power. We do have a leftover. So 7th root of q. How many q's do I have? Just 1. Again, if the index and your exponent match, that is just 1. And then we have 7th root of r to the 6th power. 1, 2, 3, 4, 5, 6. How many groups of 7 can I do? 1, 2, 3, 4, 5, 6. There are 0 groups of 7. So this is all of our leftovers. So we cannot simplify that. It stays as r to the 6th power. All right, let's go ahead and write this out. We have -3 times 7th root of 128 times 7th root of 5 times. Now, I'm looking back up here. I don't have this. I don't have this. I do have this. So instead of writing 7th root of p to the 12th, I now have, I'm simplifying here. Let's shift this up. So now I have p to the 1st power times 7th root of p to the 5th power times I have q to the 1st power times 7th root of q to the 1st power times 7th root of r to the 6th power. Now we do know what the 7th root of 128 is. That is 2. Keep the 7th root of 5. We got p to the first power, 7th root of p to the 5th power, q to the first power, 7th root of just q to the first power, times 7th root of r to the 6th power. Everything not inside the house needs to be multiplied together. So we get negative 6p to the first power, q to the first power. Everything that is inside of a house with the same house number, sometimes they'll trick you and they'll give you different indexes. Be careful. We're going to write this under one roof, one radical, 7th root of what's inside. 5 is inside, p to the 5th power is inside, q is inside, and r to the 6th power is inside. Okay, be careful on that. Write everything out. So let's go ahead and talk about your exponential properties, since we are talking about exponents. This is a brief review of what to do. So your exponential properties, if you have the same base, so all of these must have the same base. You have the multiplicative property. So if we have x to the nth power times x to the m power, that means we're going to add the exponents. If we are dividing, let's say x to the n over x to the m, you're going to be taking the top minus the bottom, subtracting. Now this one is a power to a power. If your exponent has an exponent, so let's say we have x to the n power raised to the power of m, you're going to multiply those together. If your exponent is negative, we already talked about this, exponent negative. So let's say we have x to the negative nth power. You're going to take the reciprocal of the base. Now this one again, the negative is the direction to flip base. So you're going to flip the base. So take the reciprocal of the base, keep the exponent positive. So once you flip the base, you want to make sure to make the exponent positive. Next, we have the zero exponent. This is always 1. And this is anything to the 0 power. Is 1. So these are going to be the ones that you're going to be using. Let's go ahead and apply these properties to a question from Integrated Math 2, and then I'll show you what we're doing with it in Integrated Math 3. So let's use large parentheses. We got 2x squared y negative 3 all over negative 2x y cubed times negative y, close it, and everything's being raised to the 4th power. Okay, step number 1, you are going to be bringing in, so if you have an exponent, you're going to be bringing in that exponent on every single thing. Now, there's many exponents that I'm talking about. First thing we're going to do is we're going to make a 1 onto anything that is missing for variables. You're going to take this 4 and you're going to bring it onto every single thing that you see because it is attached to everything with parentheses. So we got 2 to the power of 4, x squared to the power of 4, y to the power of negative 3 to the power of 4. We got negative 2. Let's put that in parentheses. That matters. To the power of 4. Let's put 2 in the parentheses as well. X to the first power to the power of 4. Y cubed to the power of 4. And negative y to the power of 4. There should be a missing exponent of 1 here. Now that you have brought in your exponent of 4 onto everything, let's go ahead and evaluate. So we can do things like 2, let's make parentheses, 2 to the power of 4, that's just a number, that's just 16. Negative 2 to the power of 4, also just a number, that is 16. Next, we see an exponent with an exponent, so we're going to multiply. An exponent with an exponent, we're going to multiply. It's 4 times 2 is 8. Negative 3 times 4 is negative 12. Here we got 1 times 4 is 4. 3 times 4, that's 12. And careful here, we're not really caring about that negative y. We are going to be working here. So negative y, 1 times 1 is 4. I'll show you what to do with that negative. It is a tricky little interesting step that we have to take. All right, so let's go ahead and continue to simplify. Notice that in my numerator, I have 16, x to the 8th power, y to the negative 12th power. Yes, it is negative. Negative is the last thing you need to worry about. What I want to show you is that all of these are different. X is different than y. We are unable to combine because they are unlike terms. In the denominator, we have 16 times x to the 4th power, y to the 12th power. And then notice we have this negative on y. This is different. So I'm going to rewrite this as negative 1 times y to the 4th power, which means that we need to bring in that 4 one more time. 4 goes on y, 4 goes on negative 1. Everything in the numerator stays the same. Yes, you can get rid of those 16s. If you would like, I'm going to do that a little bit later. So here now I have negative 1 to the 4th power and y to the 4th power. So if we type into the calculator, negative 1 in parentheses to the 4th power, it gives us just 1. And we can combine this 1 that we just evaluated with the 16, and it kind of just gets absorbed. So we got 16, x to the 8th power, y to the negative 12th power, all over 16, x to the 4th power, y to the 12th power, and now a positive y to the 4th power. Here, notice that we have the same bases, both in the denominator. They are being multiplied, so that means we're going to be adding those together. 16 times x to the 8th power, y to the negative 12th power, all over 16, x to the 4th power. Again, add these 4, 5, 6, so 16 here. The reason I wanted to wait to deal with those 16s, these 16s, is because when we are at this step where nothing in the numerator will combine, nothing in the denominator will combine, we are going to now divide by splitting this up. So 16 over 16 times x over x times y over y. Now, yes, we do still have a negative. Don't worry about that yet. 16 divided by 16, that's just 1. Now here, because we are dividing, our exponents are going to be subtract. Here, because we are dividing, our exponents are going to be subtracting. How this will look like, we do have that 1 times, we're going to keep that line, and we're going to bring up that denominator 4 times line. Yes, that line is important. And we're going to bring up that 16. You can start skipping that 1. We don't really need it. So 8 minus 4, we got 4. Negative 12 minus 16, careful with double negatives here. We got y to the negative 28th power. And here, after everything is all done, we're going to pick up that y, we're going to pick up that 28. Remember, the negative is directions to flip, not the 4 on x. That's not negative. So we have x to the 4th on top, y to the 28th positive on the bottom. Okay, so this is an IM2 style question where we just had integers for our exponents. Now, why is this important in IM3? Well, because in IM3, we are introducing your fractional exponents. So your exponents that will have fractions. For example, like this. Now, this is an IM3 question, so I am going to go a tad bit slower. There it is. Reminding you that you do need to understand fractions in order to be successful. You cannot have any negatives in your answer. Let's try this. Open a to the 3/2 power, v to the 1/4 power, all over open, a v squared raised to the negative 5/3 power times v times a squared. I'm going to make sure there's nothing else here. And then close it just like that. There is no exponent on the outside, so we don't have to bring everything in. Step number 1, if there was an exponent, we'd bring the exponent on everything. I do see an exponent in parentheses in my denominator, so I'm going to fix that. We're going to rewrite everything using multiplication here. Everything gets to be split up. This negative 5/3 is going to go on 2 and on a. So v squared has an exponent of negative 5/3 times v times a squared. If you have an exponent raised to an exponent like here, we're going to multiply with the help of a calculator. 2 times open negative 5/3, close it. Decimals are for sure not allowed. So you're going to press second PRB. Again, that's a mixed number. That's not allowed. So we're going to convert that. Keep the negative outside of your conversion. 3 is your denominator. 3 times 3 plus 1 is 10. So we're going to rewrite this section right here. We got a to the 3/2 power times v to the 1/4 power. This is just a to the negative 5/3 power. This is now v to the negative 10/3 power times v to the 1st power times a squared. Notice that in the denominator, I have things that can be put together. I have an a here and an a here. Yes, I do have a's in the numerator. No, I don't want to deal with those yet. And I have v here and v here. So I'm going to rearrange things. In my numerator, I have a 3/2 times v 1/4. Here I'm going to rearrange and the a's are going to be touching now. And then I'm going to rearrange and have the v's touch. Okay, to combine your a value, these are being multiplied, so that way the exponents need to be added. These bases are being multiplied, so the exponents are being added. You can do this off to the side if you like. You got negative 5/3 plus 2. Then you got negative 10/3 plus 1. And I say you can do this off to the side because this is a whole number. We can just do common denominators here and continue solving. Same thing, common denominator here and continue solving. Or if you want to cheat and do this on a calculator, that's fine. You most likely will need to convert or not. So this one we get 1/3. I did cheat and use a calculator. Let's try this, negative 10 thirds plus 1. So for example, here I get -2 and 1/3, which will need to be converted to an improper fraction. So we got negative, denominator of 3, multiply the bottom, add the top. So 6 plus 1 is 7. So what do we have in our numerator? In our numerator, we have 3/2, 1/4 v. In our denominators now, be careful. A is now to the power of 1/3. V is now to the power of -7/3. Alrighty. Now, after we have combined everything on top and bottom that we can, we're going to split it up with our A's being on top of each other and our V's being on top of each other. When you have same base that are being divided by, you're going to take the exponents and you're going to subtract these exponents. Oops, my negative. And when you do that, you want to draw a line indicating that they are right now in the numerator position, not in the denominator position. For example, here, you got to be careful with the double negative. And again, you have a choice to make. You can do this by hand, or you can do this with a calculator. I'm going to choose to do this with a calculator. So I'm typing in 3/2, must use parentheses, 1/3. That way I don't have to personally do common denominators. I can just off to the side. I have 1 and 1/6. So that means 6 plus 1 is 7. So I have A to the 7/6 power times. Here again, I'm going to use a calculator to cheat. I got, 1/4 minus a -7/3. And again, I'm going to convert to 7/12. That means I have a 12 in my denominator. 12 times 2 is 24, plus 7 is 31. Now again, these are not necessarily going to be pretty answers, but these are going to be combining things until you can't combine anymore. All right, beautiful people, thank you so much for hanging in there. We will spend class time practicing. Just a reminder, your exam on Chapter 4 is going to happen rather quickly. Please make sure that you are practicing on your own. Goodbye.